Guys, welcome to my tutorial today. Please, I will want you to subscribe to my Facebook page, subscribe to my YouTube page, also like all our videos, also follow us on TikTok. And if you want to get the full video of this tutorial, you must follow us on Facebook and also subscribe to our YouTube channel on YouTube. That's where you get the full video. The video on TikTok is not more than 5 minutes. And if you have not been following this page and you are a student, secondary school student, I think you are missing. Please do follow this page. Also refer these pages, all our pages, Facebook page and YouTube page, and also our TikTok page, to your friends, your brothers that are in secondary school, preparing for Waec, or those in SS1, SS2. There are lots of things you are going to be learning. What we do here, we teach maths, we teach physics, we teach chemistry, we solve Waec questions and we explain. We also give assignments for you to solve and trial on the subjects based on the similar questions we save, and all of them are Waec or JAM questions. All right, and you would like to support us, you can contribute your support on the account display on the screen. It is necessary you support to encourage us and to also help us to get a better quality for our video and to serve it better. All right, please refer this page to as many students as you can. There are a lot you can learn from this page, a lot. All right, today what we do is we bring a topic in a particular subject, maybe maths, chemistry, or physics. We solve JAM question, we also solve Waec question. So today we are solving, we are doing physics, and we are solving question on heat energy, Waec. So next video we are going to solve the same question on heat energy based on JAM own questions. So that's what we are doing. So today we are focusing on Waec questions in physics on heat energy. All right, and we are going to be solving 3 questions, and then I'm going to give 2 assignments. Try those assignments, put your solution on the comment section. Put your solution, not the answer, the solution, how you got it, put it on the comment section as a means of you are following, you are trying. You may not get it, you may get it, but put it there so that we'll look at it and then tell you if you get it or not. All right, and today we want to look at say a waterfall is 420 meter high. Calculate the difference in temperature of the water between the top and bottom of the waterfall. Neglect heat losses. Take G equals to 10 meters per second. Specific heat capacity of water is 4.20 times 10 raised to 3 joules kilogram per Kelvin. Okay, this question is on heat capacity. Heat capacity refers to the amount of heat energy required to raise the temperature of an object by 1 degree Celsius or 1 Kelvin. The amount of heat needed to raise an object, the temperature of an object by 1 degree Celsius or 1 Kelvin, that is heat capacity. And heat capacity, we say the quantity of heat, we represent it with capital Q, is equals to heat capacity then change in temperature. This is the formula for heat capacity. Let me divide this, heat capacity, right? And now heat capacity is dependent on mass, the amount of a substance, or the size of the object. You may see this in your question, in a JAM or Waec objective question, or even your theory. So heat capacity is dependent on the mass, amount of the object, of the substance, or the size of the object. What does that mean? It means that a body with a larger size is definitely going to have mostly have larger mass, and therefore their heat capacity will be higher also. So the higher the mass of a body, the higher the heat capacity of that body. Now the next definition we want to define, the next concept is specific heat capacity. Now specific heat capacity is the same with heat capacity, but the only difference is that we are looking at it in terms of the unit mass of that object. Don't forget, we say heat capacity is the amount of heat energy required to raise the temperature of the whole body, mass of the body, the whole mass of the body by 1 degree. While heat capacity is the amount of heat energy required to raise the temperature of 1 unit mass of that body, just 1 unit mass of it, not the whole body, by 1 degree Celsius or 1 degree Kelvin. So these are, since we say it is quantity of heat, we are looking at quantity of heat is Q, is given as a specific capacity, which is in small letter C. This one is in capital letter C. The C here, capital letter C here, is heat capacity, and of course Q is the quantity of energy, or quantity of heat. Then this one is a Cm, then change in temperature. Yes, the small c here is the specific heat capacity. M is mass, and of course Q is the quantity of energy. So that is the terms you need to know for now. So let's go back to the question. Say a waterfall is 420-meter high. Calculate the difference in temperature. So we are looking for this change in this formula I'm making use of, not this. The reason because they make reference of specific capacity, not heat capacity. Okay. Then a waterfall is 420-meter high. They gave us height. I will write my parameters. They say H is, well, let me use capital H. H is 420-meter high. Calculate the quantity of heat. Quantity of heat. Let me use, I've used capital T before. Change in heat, which is equal to, that's what we're looking for. Now, they say we should neglect heat capacity, the heat losses. Then they now give us acceleration due to gravity, which is G, to be 10 meters per second square. And then they gave us specific capacity, which is 4.20 times 10 raised by 3 joules kilogram per Kelvin. All right, so how do you solve this question? That means the water has been stored up before. So there are some terms that we're also going to defend. That water body was possessed an energy when it was at height. You know, at that particular height, it possesses an energy, and that energy is what we call potential energy. So it's what I'm going to also quickly explain here. Like I said, if you are not following my tutorial, you're going to be missing a lot. Please bring all your friends or brothers or sisters or anybody you know that are in secondary school. Let them follow this class. We teach maths, chemistry, and physics, Waec and JAM. What we explain. Okay, potential energy. We say potential energy is energy stored in an object due to its position. Due to its position, energy stored in an object due to its position. So, and potential energy, we can look at it from two ways. Number one is the gravitational potential energy. Gravitational potential energy. Now, what's gravitational potential energy? Gravitational potential energy is the energy stored due to its height above the Earth's surface. Due to its height above the Earth's surface. Okay, you hear the word gravitational. You should know they're talking about height. So the energy stored due to its height above the Earth's surface, and the formula is potential energy equals to mgh. mgh. Let's use small letter to explain that is you're talking about the height of the object out of the object. Okay, mgh, where m is mass, g is acceleration to gravity, h is height. Then the next potential energy is what we call elastic potential energy. Elastic potential energy. Now, this elastic potential energy is the energy stored that can be stretched or compressed, just like you find in spring, energy stored in spring. So that's potential energy, and that one formula is given as half ks square to move, and that's why we take us to the next kind of energy, which is known as the kinetic energy. Now, the kinetic energy is the energy of an object possessed due to its motion. So when the energy is in motion, you know, and kinetic energy is dependent on two factors, which is the motion and the velocity. Therefore, kinetic energy is equal to half mv square. Half mv square. Half mv square. So you need to know all this. So you need to know all this, because without this knowledge, you won't be able to get this particular question. Say a waterfall is 420-meter high. Calculate the difference in temperature of the water between the top and the bottom. Top and bottom. So which energy are they talking about here? Is it potential or kinetic? The simple answer is that energy is a gravitational potential energy. It's a gravitational potential energy because that body was at rest, was in its position, stored at the top before it fell. So it's a potential energy. So we are going to say the energy stored is equal to potential energy, or you say gravitational potential energy, as the case may be. Energy stored is equal to what? Potential energy. So since they're talking about energy here, so, and don't forget, in our specific capacity, we say energy, quantity of energy is equal to what? MC or Cm, change in temperature. And then potential energy is equal to what? mgh. And if it is true, this is energy, and they are equal, that means we will be right to say MC, change in temperature, is equal to mgh. So what are they asking us to find from the question? Change in temperature, which is this. So we are going to make this sort of formula, and in making that sort of formula, we have change in temperature equals to mgh over mc. Right? So now we can see that mass, we cancel mass. Then we now have change in temperature equals to gh over c. So all these parameters, we know them. So we'll go straight to substitute. So g is 10 times height is 420. Now this 420 meter, we need to convert it because from the question, okay, all right, we can work with it that way. You can work with it that way because acceleration due to gravity itself is in meter. So we say 420 divided by specific capacity, which is 4.20 times 10 raised to the power 3. All right. So how do we do this? If we subtract this, if we add this 0 to this, we are going to have 4200 over 4.20 times 10 raised to the power 3, right? And if you make this, put this numerator to 1 to, we are going to move this point here 1 2 3, so we are going to have 4.2 times 10 raised to the power 3, and also 4.2 times 10 raised to the power 3. So you can see they can cancel out. This here 1, this here 1. So we now have change in temperature equals to what? 1 degree Celsius, and that's the answer. You can see the answer is B. All right, let's go straight to solve the second question. By the way, the first question we solve, the question is Waec 1998, and then the second question we are solving is 2014, and the question says the mass of an empty density bottle is 30 gram when filled with a liquid. The mass of the bottle and the liquid is 40 gram. On heating the filled bottle to 40 degrees, the mass reduces to 38 gram. Calculate the apparent cubic centimeter of the liquid. Let's go straight to the solution. Now, there's something you need to know about cubic expansivity. Cubic expansivity is the amount, is the change in volume of a material, you know, per rise or per degree rise in temperature. You know, that is cubic expansivity. So, let's go straight to the point to solving this. So now we now say apparent. Here now they're asking us for the apparent cubic expansivity. Now from the question, we will say the mass of hot liquid, expelled over mass of hot liquid left times degree rise in temperature. Okay, mass of hot liquid expelled all over mass of hot liquid left times degree rise in temperature. Now, what is the mass of hot liquid expelled? Mass of hot liquid expelled now is equals to mass of bottle and liquid minus mass left after heating, and that will be mass of bottle and liquid. If you go back to the question, it's stated there, say the mass of the bottle and liquid is 40 gram. That is 40 gram, right? So now we now go to mass of liquid left after heating. Mass of liquid left after heating. This 40 gram is mass of bottle and liquid, right? Then now the mass of liquid left after heating. Mass of liquid left after heating is 38 degrees. It's stated there from the question. They said the mass reduces to 28. It was 40 degrees before. Then after heating, it now reduces to 38 gram. So the mass of liquid left after heating is 38 gram. Then mass of hot liquid left. Mass of hot liquid left is equals to the mass of hot liquid left is equals to mass left after heating, the mass of liquid left after heating minus mass of empty bottle. So I'll say mass of liquid left after heating minus mass of empty bottle. Mass of empty bottle, and that will give us mass of liquid left after heating, of course you know, is 38 gram. Then mass of empty bottle is stated on the question. The first sentence then say the mass of empty bottle, the empty density bottle is 30 gram. So mass of empty bottle is 30 gram. This one is mass of liquid left after heating. So this is what it is. So our formula initially we say apparent cubic expansivity is equals to mass of hot liquid expelled all over mass of hot liquid left, and we have stated that mass of hot liquid left is mass of bottle and liquid minus mass of mass left after heating. So the formula, total formula now will now become apparent cubic expansivity is equals to, I'm going to put this for now, I'll say mass of bottle and liquid minus mass of liquid left after heating all this one here represent the mass of liquid expelled. That's this one. Then for down here we now have mass of hot liquid left. The mass of hot liquid left will now become where is it? Mass of hot liquid left will now become mass of liquid left after heating minus mass of empty bottle. So it's a mass of liquid left after heating minus mass of empty bottle, then times degree rise in temperature. So if we have to substitute all this, which we have got here, so mass of liquid left after heating, mass of liquid left, mass of bottle and liquid, which is 40, mass of bottle and liquid is here, so we'll go straight to put it, 40 minus mass of liquid left after heating, mass of liquid left after heating, which is 38, so I'm going to write it, 38, all over, mass of liquid left after heating, which is 38, minus mass of empty bottle, which is 30, then times degree rise in temperature. From the question, what's degree rise in temperature? Degree rise in temperature is 40 degree, okay, 40 degree, right? Okay, so this is what we get. So we are going to say 40 minus 38, which is 2, 38 minus 30, which is 8 times 40, 8 times 40, right? So 8 times 40, which is 2 divided by 320, then 2 divided by 320, which will give us 0.00625 per Kelvin. So but if you can see from the question that this is not fine, so we'll make this we'll put this in 2 decimal places. So in doing that, we'll move this point in between 2, 6 and 2. If you do that, you're going to have 6.25 times 10 raised to power minus 3 per Kelvin, and this is our answer. And you can see the answer is B. Okay, let's go to the next question. All right, the next question is Waec 1997 on same heat energy. And this question is on linear expansivity. The first question is on heat capacity, specific capacity. The second question we solved today was on cubic expansivity. This time around is on linear expansivity. So the 60 bars each of 3 meter length 3 meter at 28 degrees Celsius are to be used for constructing a rail line. If the linear expansivity of the steel is 1 times 10 raised to power minus 5 per Kelvin, what is the safety gap that must be left between the successive bars if the highest temperature expected is 40 degrees? This is actually a very simple and straightforward question. And just as we defined cubic expansivity, linear expansivity is a change in the length of a material per unit rise in temperature, meaning that as the temperature of a material rises or increases, the length of that material tends to also increase. So as a result, we will have when the length of the material is in its original length and when it has expanded to its new length, and then we are going to have also the temperature when it is in its original length and the temperature when that makes it to rise to its final length. All this must be there. Therefore, we say linear expansivity is equals to change in length all over original length change in temperature. And don't forget that change in length is equals to what? Final length minus original length. Final length minus original length. Likewise, change in temperature is the final temperature minus the original temperature. That's the initial temperature. You know. All right. So, but this time around, the question says we should look for the safety gap that must be left. What are we looking for? Is it this linear expansivity? Is it original length? Is it change in temperature? Or is it final length? Or is it final temperature? Is it original temperature? Initial temperature? What are we looking for? So safety gap. They're talking about distance. They're talking about length. What is that change in temperature? Increase in temperature. Let's assume the real is this. You know, this is the real. So the when the temperature was 28 degrees Celsius, the length of this real is 3 meters. And by the time the temperature rises to 40, this 3 meters is when it's 28 degrees. By the time it rises to 40 degrees, the length now increases little when it rises to 40 degrees. So this increase in length is what we want to look at. This increase in length, this place X, that's what we want to look at. And this place here is what we call change in length. Change in length, because this is the final length and then this is the initial length. So if you subtract this final length from this initial length, then this is the final length start from here to here. If you subtract all this from this, you're going to be left with this change in length, and that's what we're looking for, change in length. So by doing that, we are going to make change in length such a formula. We are going to say change in length is equals to alpha original length change in theta, and then we are going to say alpha original length, because alpha is linear expansivity, change in theta is what? Final theta minus initial theta. If you like, say theta 2 minus theta 1, anyhow you want to use it, as long as you define it in your solution, there's no problem. So all right, so we are going to say change in length, which equals to linear expansivity, which is alpha original length, then final temperature minus initial temperature. You can say theta temperature 1, theta 2 minus theta 1, as the case must be, as long as you explain it. And then in substituting, we're going to say alpha is 1 times 10 raised to minus 5 times original length, which is 3 meters. If you go through the equation, you discover that the length is given in centimeter, so we need to convert that 3 meters to centimeter, and do that we multiply by 100. Then final temperature, which is 40, initial temperature is 28. So anything multiplied by 1 is 1, so I'm going to say 10 raised to minus 5 times 3 times 10 raised to 2 in standard form, times 40 minus 28 will give you 12. And then if you multiply 3 by 12, you have 36 times 10 raised to minus 5 times 10 raised to 2. We will apply the law of indices here. Last class we taught of the law of indices. If you have not followed last class in maths, please do go through our questions and solutions we have solved and follow them. So we're going to have 36 times 10 raised to minus 3. And then if we convert this to one decimal point, you're going to have, move the point here to this place, you're going to become 3.6 times 10 raised to 1 times 10 raised to minus 3. If you also apply the law of indices here, you're going to have 3.6 times 10 raised to minus 2 centimeter. And then this is our answer. As you can see, the answer is D. All right. Thank you for following this tutorial. Please, if you have not followed our page, follow our Facebook page, follow our YouTube page, follow our TikTok page, and also support us financially. Any amount you have will go a long way to see that we do a better video and to encourage us. And also, please, there's an assignment on this video. Comment your solution, not just the answer, your solution on the comment section. We will going to look at it and then tell you if you get it or not. Don't forget, attempting the assignment is a sure way to get yourself improved and to show that you understand the concept. Thank you. See you next class. In next class, we're going to look at the 7 hit question on jump questions. The one we solved today